Today we'll analyze the merge sort algorithm using big O. And given an array of numbers that need to be sorted, see here we have the number of elements being 8. This array gets recursively broken up into arrays that are half the length. And that keeps going on until we reach a stopping condition where we have separate arrays with one element in them. And then next comes the merge operation. And to analyze the merge operation, we'll start with a couple of examples to see how it works and determine a worst case. So given two already sorted lists, the merge operation starts by comparing the first elements, and 1 is less than 5, so 1 gets placed in the merged array. And the iterator shifts to the right in the first array. And then 2 gets compared with 5, and 2 is less than 5, so 2 gets placed in the merged array, and the iterator shifts to the right. And then 3 gets compared with 5, and 3 gets placed in the merged array. And again the iterator shifts to the right, and then 4 gets compared with 5, and 4 is less than 5, so that gets placed in the merged array, and we run out of elements in the first array to compare. And therefore the next step in the merge algorithm is to place the remaining elements in the merged array. So where all the numbers in the first array are smaller than those in the second array, we required 4 comparisons. Now consider this case where we have 1, 3, 5, 7 and 2, 4, 6, 8 in the two sorted arrays. So again we compare the first elements, and 1 is less than 2, so it gets placed in the merged array, and the iterator shifts to the right, and then 3 gets compared with 2, and 2 is less than 3, so 2 gets placed in a merged array, and the iterator shifts to the right in the second array. And now 3 gets compared with 4, so 3 is less than 4, and therefore the iterator shifts in the left array. And then 5 gets compared with 4, 4 is less than 5, and therefore the iterator shifts in the right array. And 5 gets compared with 6, 5 is less than 6, so the iterator shifts to the final element. And then 7 gets compared with 6, and 6 is less than 7, so the iterator shifts to the right. And then 7 gets compared with 8, 7 is less than 8, and there's no more elements left to compare, so therefore the 8 gets placed in the array. So in this second case, we required 7 comparisons. And this here is the worst case. So in general, to merge two lists with n elements, so in this case we have n equals 4, we required at least n comparisons, and at most 7 comparisons, so that will be 2 by n minus 1 comparisons. And now we go back to our merge sort algorithm, being a divide and conquer or divide and merge algorithm. So we've completed the divide stage, where the array gets broken up into subarrays recursively. And then we get to the merge part of the algorithm. So here we get each of the two arrays being merged. So we get 1, 5, 3, 7, and so on. So what we got is 4 merges, which is 2 squared, multiplied by 1 comparison, required for each merge. So noting our merge algorithm here. And then these subarrays get merged. So what we get is 1, 3, 5, 7, and 2, 4, 6, 8. And this is done using the merge algorithm which we just covered. So as we saw in the worst case, we required 2n minus 1 comparisons. So here we had 2 merge operations and 2n minus 1 comparisons. So that would be 3 comparisons for each. Given the length of each subarray is 2, so 2 by 2 minus 1 in the worst case. And then finally, we merge these 2 arrays in the final array. So we get 1, 2, 3, 4, 5, 6, 7, 8. So what we got is 1 merge, which is 2 to the 0, and the number of comparisons is 2n minus 1. So 2 by 4 is 8, minus 1 is 7 comparisons. So generally, to write our recurrence relation, we have m and the subscript is 2 to the k, and 2 to the k is equal to the number of elements. So in other words, in this case, k is equal to 3. And this is the total number of comparisons. So first we have 2 to the power of k minus 1 gives 2. By 1 comparison, and then plus 2 to the k minus 2 by 3 comparisons, and then plus 2 to the k minus 3 by 7 comparisons. And in general, this keeps going on and on until we obtain one merge operation, multiply by 2 to the power of k, which is 8 in this case, minus 1 is 7 comparisons. And we'll add another term in, so what we have here is previously 2 merges, and multiply by 2 to the k minus 1 minus 1 comparison. So in this case that would be 2 squared minus 1. And therefore m with subscript 2 to the power of k minus 1 is equal to 2 to the k minus 2 by 1 plus 2 to the k minus 3 by 3 and plus 2 to the k minus 4 by 7 and so on, and then plus 2 by 2 to the k minus 2 minus 1, and finally we have 1 by 2 to the k minus 1 minus 1. And now if we multiply this second sum by 2, we get 2 by 2 to the k minus 2, which gives k to the minus 1. Then 2 to the power of 1 by 2 to the k minus 3 gives k to the minus 2, and so on. And this term here becomes 2 by 2, which is 4. And this one here becomes 1 by 2. And now if we have m subscript 2 to the k minus 2m subscript 2 to the k minus 1, well, this cancels with this cancels with this, and this term cancels with this, and finally this term cancels with this one, and this one here will cancel with the previous one. And what we're left with is 1 by 2 to the k minus 1. And now we can solve this recurrence relation. And if we use a dummy variable, so letting s with subscript k equal m subscript 2 to the k, We can now write our recurrence relation as sk minus 2sk minus 1 is 2 to the k minus 1. And our initial condition in this case would be S0, which is m subscript 2 to the 0, which is m1, and that's equal to 0. Because when k is 0, we have an array with a length of 1, and you can't split that array further, so you thereby have 0 comparisons. And we can say that this is a first order non-homogeneous recurrence relation. So the homogeneous solution is simply some constant multiplied by this constant raised to the power k. And for the particular solution, we choose a similar form to this function g of n. So we have a constant by k by 2 to the k, because this 2 to the k appears in the homogeneous solution, and we thereby multiply by k, and plus another constant. And now if you substitute this in our recurrence relation, so what we get is bk by 2 to the k plus c minus 2 by b by k minus 1 by 2 to the k minus 1 plus c. And that's the left hand side, which we equate with the right hand side. And if we expand these terms, we get bk by 2 to the k plus c minus 2bk by 2 to the k minus 1. Then minus minus is a plus, so that will be plus 2b by 2 to the k minus 1. And then minus 2 by c is minus 2c. And that's equal to the right hand side. And therefore we have bk by 2 to the k plus c. Then we have minus bk, and 2 to the power of 1 by 2 to the k minus 1 is 2 to the k. And similarly, we have b by 2 to the k minus 2c is equal to 2 to the k minus 1. So these two terms cancel, and we're left with b by 2 to the k plus c minus 2c is equal to 2 to the k minus 1. So if we equate coefficients, we see that b is equal to 1 and c is also equal to 1. And therefore the general solution to our recurrence relation is a superposition of the homogeneous and particular solutions. So we have sk is a by 2 to the k plus k by 2 to the k plus 1. And applying our initial condition, S0 is 0, we have a by 2 to the 0 plus 0 plus 1. So that means a is minus 1. So here we have minus 2 to the k. And remember that sk was m subscript 2 to the k. So therefore, we can write sk as m subscript 2 to the k. And if you recall, 2 to the k is the number of elements in the array. So we can further write this down as mn is minus n, which is 2 to the k, and then plus k by 2 to the k. So 2 to the k is n, and k, which you can obtain by taking the log of both sides. So you'd get k is log n plus 1. And therefore the time complexity of the merge sort algorithm is O(n) log n, given that n log n is the fastest growing term. Please subscribe, like and comment to help me reach more students.